we start all over again. That what we have done so far is FDM, that is called finite difference method. So it should be very clear to you. FDM is what? Finite difference method. Okay. And we had done the derivations for all these. What we did, different types of differentials, we converted them using some technique which is called finite difference method, and the same can be used to discretize the equations. Now we are moving on to this finite volume method. In the finite volume method, first we talk about what is the difference between the two, that is, okay, so in a FDM method, the equation for the center point is written in terms of the neighboring points. Now you can recall that if you want to write equation for this, we are writing in terms of point this and this. When we were talking about del phi by del x, this was equal to, you can say, phi I plus 1 minus phi I minus 1 divided by delta x, twice delta x. So you are going right point, you are going to left point, and you are doing same thing when you want to find out del phi by del y. You can do it phi j plus 1 minus phi j minus 1 divided by twice delta y. This is what. So equation at a particular point is written in terms of the neighboring points. Okay. Now when we are talking about FVM, okay, FVM, then what happens, this computational domain is divided into volumes. Okay, so we will talk not in terms of the points or the nodes, we will talk in terms of the volume. So this is the volume we will be talking about, and it can be of any shape. Just to, at this moment, this is the volume. So we are not talking about these points, this point, this point, this point, this point, etc. Right? We are talking about the whole volume, and that is why it is called finite volume method. And in finite volume method, what is done, the computational domain is subdivided into finite number of volumes. Now, unlike in FDM, the whole domain, you put nodes there, you put points there, okay, and of course you can join them and say that it is divided into volumes. But we have no such concept, the volumes are not there, okay, because we are not using them. You can make them, that you can select certain points and you can say this is the volume, okay, but that concept we are not using. While we are talking about FVM, we talk in terms of volumes. And now remember here, it is a 2D figures, both the cases it was a 2D figure. And when we talk in terms of volume, that means we are assuming that there is a depth of 1 meter or so, unit depth is there. Okay, just because it is difficult to make representation on 3D, we are doing it on 2D. Okay, so if the same thing, if this thing is expanded, if you are talking about this as a 2D, but it's not actually a 2D, it is a 3D, third dimension we are not talking about. And we can take it as a uniform, a flow which is only in 2D, that means there is no variation in the third direction, can still be taken as a flow in a volume. Okay, so there is a depth in it. Now that is what I was saying, you have a points here, you can say this is a volume, multiply by the depth, this is area, multiply by depth, you get the volume. Okay, so the whole thing is divided into volumes, but really we are not using in terms of volume, and that is why we call it only FDM. Okay, now the same thing when you do in terms of finite volume method, we will talk about this volume. Okay, this is the only. Points can be similar. Now, okay, subsequently, the conservation equations are discretized in such a way that the resultant equations express conservation of the relevant physical quantity for each of the control volume. Now let us understand what it is. In FDM also we started with the conservation equation. Okay, then we discretized it. Okay, and we can apply now to different points. Now when we are talking about the points, conservation doesn't mean anything, because conservation, the first requirement is you should have a volume, right? So FDM equations have started from the conservation equation only, because CFD equations are all conservation equations. The same conservation equation we have used, we have converted them into algebraic equation, and now we are applying at each point. So the conservation at each point is maintained or not, we don't know. Okay, we started with conservation equation, but when we are applying it, the conservation is, because we have actually made approximations, we have made truncation errors, we have removed truncation error, which means our algebraic equations are not same as our differential equation. So we cannot say that our equations are enforcing conservation. They are no longer conservation equation. Are you getting the point? Let me just highlight it again here. You have partial differential equation, right? It is converted to FDE, finite difference equation. These are your conservation equation, and this is approximate because there is truncation error here, which you have made it equal to 0. So this equation need not be conservation equation. Is it a conservation equation? No. We don't know. We have changed the equation. So that is what we are saying here. So subsequently, the conservation equation are discretized in such a way that the resultant equation express the conservation of relevant physical quantity for each of the control volume. What does it mean? That now we are applying the equation in a FVM, finite volume method. At each volume, the conservation is maintained. This is what the difference is between the two. Okay. The conservation equation for a physical quantity for a cell is written in terms of accumulation, advection, diffusion, and generation of physical quantity. So now when we are talking about, we will come back to the same concept of the 4 terms: accumulation, advection, diffusion, and generation. Because whenever there is a volume, something is entering in, something is going out, you can talk in terms of that. Okay. Now, what is the advantages of FVM? What advantages? There are 2 major advantages, okay, that the final volume method holds over finite difference method. It has a good conservation properties from a physical point of view, as the conservation equations are discretized in such a way that the conservation equations are applied to each of the control volume. Now you see the difference. In finite volume method, you will find the conservation equation is applied at each cell, where in FDM you start with conservation equation, but you don't know what is happening on the way. So in a way, your conservation of properties, which is a basic law, so your physics is applied to the smallest volume. So this is one beauty of FVM, or you can say one strength of FVM, that the physical law, your physics law, which are the governing laws, they remain applicable at the level of the volume, smallest volume. Okay. Now, the second advantage is it allows the discretization of the complicated physical domains without resorting to the transformation of equation to generalized coordinates. Now, what happens is, we'll talk more about it, that when you have a domain which is a complicated domain and you cannot divide that domain into proper structure grids, then if you are talking about FDM, in FDM you have to have structure grids. So you will have to use generalized coordinates. We will talk what is the generalized coordinates. In generalized coordinates, we make a irregular shape into rectangular shape or some, let's say, rectangular shape, right? So, but in case of FVM, you don't have to do, you can go for unstructured grids. So for FDM, you require a structure grid. For FVM, you don't require a structure grid. This is the basic advantage with the FVM. Okay. And most of the, you can say, the programs or the solutions are using FVM. FVM is the most popular method for CFD. Now, as the finite volume method works with the control volume and not the grid intersection point, it can accommodate any grid. Same thing it is saying, that because you are talking about finite volumes, you don't have to have a structure grid. You can have any way you can form it. Okay. And in finite volume method, you can have both structure grid as well as unstructured grid. Both can be done. Only thing is you require volumes. Okay. And of course, in 2D, you require areas. You will talk in terms of areas.
Structured और unstructured grid में difference मतलब कैसे क्या होता है?
नहीं, unstructured, we talked about it, that unstructured और structured में difference ये है, unstructured में points are random. Your जो nodes हैं, they are random. You can put them anywhere. If you are doing that, what does that mean? That you have to note the coordinates of each one of them, because there is no relation between one point and the other point. In structure grids, these points are correlated. So from one point, you can find what is the coordinates of the next point and the next point of the next. If you are able to find some formula by which you can identify all the points or capture all the points, then it is a structure grid. If you have to give the coordinates of all the points, then it is unstructured grid. That means there is no correlation between them. That's the only thing. Okay. So we have unstructured mesh offers greater facility. Now, advantage of unstructured mesh is that you have greater facility for handling complex geometries. They do not require transformation of the equation into body fitted coordinate system as is required for the structure grid in finite difference method. So in finite difference method, what happens that if your shape is irregular, you can develop generalized coordinates, and using generalized coordinates you can convert it into a structured form and use that. So that type of thing is there. It will become clear when we see the next diagram. A typical representation of structured and unstructured grids for finite volume elements in 2 dimensionals is shown in figure below. Now you look at this figure. This is a irregular shape, right? The shape is, this is the shape, right? Now, if you want to find the structure grid in this, you have to put, which is called logical squares, or you can say logical rectangles. Now, what we have done, we have actually created here these types of, these are the coordinates. You can say generalized coordinates. Your axis, your axis have a curve or a different shape. So it's something like that. Your axes are not like this. Your axis can be like this and like this. You can have curves as the coordinates, as the axis. Okay, so when you want these squares, what will happen? The squares will come like this. This type of shape you can, so this type of shape at this end you can capture with the help of curved coordinates, and this becomes a logical rectangle, right? So by this you can make a structure grid, and this is how you can cover the whole of the volume. So this is one of the approach. Now if you want to go for FDM, you have to do this. Okay, FVM can take this because these are volumes also. Each one of them is a volume, right? You can apply FVM here, right? But the same thing you can do it like this. Now this is unstructured grid. You have put points as per your wish, right? And now no points are related to each other, but you still have volumes here, right? And you can pick up each volume and you can fill it up with the equation. So, but here if you want to apply FDM, you cannot. The only option available to you is either use curvilinear coordinates or divide the zone such a way that it is made up of squares and rectangles, something like that, and for the remaining portion you apply special techniques and do it. Most of the area, you like this whole thing, you can, let us say your shape is like this, okay? Now one way is that I make it a curvilinear coordinates, or let us say, why not we take about my shape is like this. Zoom. Now I want to apply FDM here. XY coordinates cannot be fitted here. What I can do, I can divide it like this, and in this area I can apply FDM. Then I can make this, let us say this area something like that, this becomes logical rectangle. I can apply here, right? Again this will become logical, this will become logical, right? Then this thing will be left, and what I can do, I can either start it very small or I do it with some different method. So I can break it, and that becomes rather complex. While this problem will not be there in FVM. You divide the volumes like this, you can fill that area with triangles. Filling with squares, triangles will be left. But with filling with triangles, nothing will be left. So whole of the area will be covered. This is the basic problem. Okay. So this you can do unstructured. This is any type of you can use. Now what are the disadvantages of FVM? So we talked about two advantages. One was that, first one, that our conservation equation is applied as it is to the smallest volume. Okay. So the physics is going down to the smallest volume. In case of FDM, you are using conservation equation, so it may happen that in one side there is a non-conservation plus some generation is there. On the other side, there is a you can say annihilation is there. They together become, you can say, conserved. But when you talk of FVM, at each point there will be no annihilation and no generation. Okay. But what are the disadvantages? The second was the structured and unstructured grid, right? Now, what are the disadvantages? All the flow parameters are evaluated at the centroid. So, what centroid means? Suppose you have this as the element, or you have this as the element. Normally, you'll have square or triangle elements. So, the values are estimated at this point. Even when you have your nodes are here, right? So, in FDM, you go by points, nodes and nodes. In FVM, because you have to talk about volume, you have to talk about these points. So, you are talking in terms of nodes, and I don't think this is a negative point. Wherever you are taking, because that is not a, but he's saying that there is a all the flow parameters are evaluated at centroid of the control volume, and interpolation is required to express variable values at the control volume surface in terms of central volumes. Now what happens is, when you are talking about this let me go back to this. When you are talking about this as a cell, and we are talking about FVM here, right? So we have to take the value at this point, we have to find value at this point, we have to find value at this point, because fluxes means something is coming in from here, something is, right? So for a cell, you need a value at the boundaries also, at the centroid also. Centroid gives the average value of that cell, boundaries gives you the fluxes, what is going in and what is going out. Now, if you want to find the value at this point, so if you want to find value at this point, this is found in terms of these average. This is what it is saying, that you require both values at the centroid of the volume, center point, and on the center of the centroid of the surfaces, because there you have to calculate the flux. Okay, so this is one disadvantage. I won't say this is a disadvantage, because this is one thing you have to follow. One disadvantage of this method, now this is the technique we have, but what is the disadvantage of this technique, that now comes in. The one method of disadvantage compared to the finite difference scheme is that higher order differencing approximation greater than the second order are more difficult to develop in 3 dimensions. Now what happens is, because FVM has 2 levels of approximations, one is interpolation and the second is integration. So what is happening is, this will become clear to you when you solve the problem, that you have an integral equation, you have a differential equation of conservation. Now when you apply that at a volume, what is going to happen? You are going to use a differential in an integral form. And integral will also be, it's not infinitely small elements. You will talk in terms of finite elements. So integral, when it is written in terms of finite values, there will be error, right? So one approximation is here that differential equation is integrated, no problem. That is for exact. Mathematics is exact. Differential equation you can make integration, no problem. Both are exact. But when you apply the integral equation to the physically, then how do you do the integration? In parts, right? Small sections. Now, real integration is that for infinitely small parts. That you cannot do. So, you are doing it for finite parts. So, there is some error, some approximation is there. So, because your integral equation is applied to a cell as a uniform, because what happens? Integration में मैं थोड़ा मैथमेटिक्स में ज़्यादा जा रहा हूँ. Let's see this. If you have been asked to find the area of under this curve. Integral, सीधा area is equal to f dx integral. Now how do you do it? You actually divide it like this. Right? Now wherever you are taking, you sum it up. Now if you are taking finite thing, there is always an error. So integral, when applied to a smaller part and it is finite, there will be some error. So that error is there. Okay. Then there is another error that is of interpolation. Because now you want to find out values at the center of the surfaces. So another interpolation is there. So you have one interpolation and one approximation for a finite parts. Now when both of these come up, it becomes slightly complex and you cannot really say what is the order of your error. How do you know that it's a second order, third order, fourth order? While in FDM, it is possible for you to keep on increasing the order. Only thing you have to take more number of points on the left and the right. We have just given for example that central difference, left and right point you take, the error is of the order 2. You could have take 2 points on the right and 2 on the left, your error will still go lower. So you have a possibility of reducing the error as much as you want. But here you don't know. That calculations become really tough. Because there are two types of interpolation and approximation already existing, and from there you have to find out what is the order of error, which is not in your control. So it becomes confusing, complicated. Only thing available to you is that whatever the truncation error is, reduce the size of the domain or cell so that your error becomes smaller. So this is the one problem with. Okay. Then how do we do it? Can I take 10 minutes? So that why I want this 10 minutes is because I could have stopped here. Because whatever I have told you will become crystallized after we do this. So otherwise it will remain only conceptual talk. Okay. So now we are doing discretization of first order partial differential. That is what we will do. Now there is one thing you have to remember. In case of FVM, this is our domain. It can be of any shape. For simplicity, it is made up of straight lines. It can be hexagon, pentagon, octagon, whatever it you want. Smallest will be triangle. The next best is quadrilateral. Okay. Now, so we are starting with the smallest one. Now, we will be coming across this notion that there is a surface, and this surface I have extended here, blown up. This surface has two components. One is area in x direction, one is area in y direction. So it is written as A1 superscript x, A1 superscript y. So this area is actually one area this and one this, and you know area is a vector. So these are two components of the area. One is in the right direction, x direction, one in the y direction. Okay. Now, the cornerstone of the finite volume method is the control volume integration. Consider cell having small volume delta VL. Okay. Now consider any type of cell. We are starting with triangle. To make it simple, you can take any one. Having n surfaces, 3 onwards, anything. Okay. Diagram above a 2-dimensional domain. The cell is a triangle. Consequently, n is equal to 3. So 3 surfaces, n will be equal to 3. Now what do? We find these derivatives, del phi by del x and del phi by del y. We want to find out at point I. Okay. Now they are measured at the center of the surface AI. तो सरफेस की जो सेंटर है AI सरफेस है, उसके सेंटर के ऊपर हम ये डेरिवेटिव्स नाप रहे हैं. तो क्या करना है हमने को? These are the projections. We have talked about it in x direction and y direction. Now, as per Gauss theorem, you can write this integral as a surface integral. So volume integral can be converted to surface integral with certain conditions. Those are singularity conditions, and they are always mostly applicable, right? Now, what do? So on the left side is volume VL, on the right side the 3 surfaces of that volume. So if you want to find out the integral, volume integral, you can do the surface integral and you can find it out, Gauss theorem. Now what we are doing, we are assuming that delta VL is very small, because this is true, this is a proper integral. VL can be of any size. The only thing is, on the left side you will break up VL into very small volumes. On the right side you will break up the surface of that volume into very small surfaces, infinitely small surfaces. That we will not be able to do. We require finite. So what we do, we make a very small cell. Now if we take a small cell, we can say that divergence of V in that cell is constant. So we take out this divergence here. So this integral becomes divergence of V into delta VL, where delta VL is approaching to 0. So that we have done here, divergence of V 1 by delta VL. So okay, the same thing we have written here, the same integral here is written here like that. Okay, only thing, there should have been 3 lines here, but we can write anyway. Now we assume that this vector V is made up of phi, 0, 2-dimensional. So divergence of V will be what? V will be equal to del phi by del x. Okay, because the second is 0. Now so you can write del phi by del x is equal to this much, and this is equal to nothing but this. Now this thing, you can, when you integrate this V is what? Phi, 0, the second parameter, and this area would become, there are 2 areas, AX and AY. Okay. Now if you do this integral, because AY is AY has to be multiplied by this, that is a 0. So you get only these two terms. ये जो है so this thing goes away, second term goes away. Now this integral is nothing but this. Summation में you are converting summation. Here the approximation is entering. Your integral is becoming summation. Okay. Now AY and AX are the projection of this surface in y direction. Okay. Phi I is measured at the center of surfaces AI, and N denotes the number of things. Okay. So this can be for a journal. This is a journal relation. You are finding at the center of the surface, and you can break up that surface into number of components and you can find this. Okay. Now similarly, if you want to find out this del phi by del y, you can find out like this. Okay. Now what we do, so what we have done, we have actually converted the derivative, partial derivative, into a algebraic series. See, on the right side is algebraic series. Same thing we are doing in FDM. But here we do not know what is the order of truncation error. That's the only thing. Right? And it will be difficult to find out actually what is the truncation error here. There it was simple because it was Taylor series. Here you are doing summation. Okay. Now we apply this to this equation. And once you apply this equation to del u by del x, you can, okay. Now we take now we take this problem. So what we are finding, that we are finding at this point, we are finding solving this equation, del u by del x plus del u by del y over del v by del y is equal to 0. I think यही इक्वेशन है ना. ठीक है. और इसको हम यहाँ पर लगा रहे हैं इस पॉइंट के ऊपर, P के ऊपर. अब P जो है हमारा एक वॉल्यूम है और इसके चारों ओर सेल हैं. नाउ द वे टू नॉर्मल वे ऑफ रिप्रेजेंटिंग दिस सेल इज north, south, east, west. That is easy to remember that whether you are on the left side or on the right side. You could have done 1, 2, 3, 4 also, but traditionally we talk about north, south, east, west. Okay. So there is a point P. On the east side of it is a point which is called E. On the north is a point which is called N. On the south there is a point which is called south, and on the west there is a point which is called W. And these are all the centroids of the volumes on that side. Okay. Now del u by del x is equal to this. Now you are finding at point P del u by del x. It is evaluated at what? On all the four surfaces you have to find this integral. Del u by del x is being found out at the centroid of point P, and you have to take all the surfaces around it and find the values of ui and aix. Now what will happen here? These two values will go away. Okay, because if you are talking about u, so you have surfaces on the right and the left. Okay. So, okay, sorry. So these are the four surfaces. So four surfaces are AE, A West, A North and AS. and you have to take x component of all of them. Now you find that the this surfaces, your north and south, they are horizontal, north and south. They have no component in x direction. So these two terms will go away. Sorry, these two terms will go away. Similarly, if you find del v by del y, it is also summation of vi multiplied by ai in y direction at 4 points. Now here, if you take east and west, these two terms will go away because they don't have any component in y direction. They have only component, only n and s have component in y direction. Okay. Now you just sum it up, right? You will get, now what is UE? UE, this is the interpolation. UE is actually the value at this point. This is the, because for finding derivative at the centroid, you are finding this area and value of function at this point. This area and value of function at this point. This area, value of function at this point. This area and value of function at this point. Now value of this point is actually average of these two. Similarly, you can talk about others also. So UE will be, UE is the point on the east surface. It will be average of UP plus UE by 2. Similarly, on the west surface, it will be UP plus UW by 2. North surface, it will be VP plus VN by 2. South surface, VP plus VS by 2. Okay. Now, this area value is equal to AEX. These values are equal to delta Y and these are equal to delta X. You put these values, you get this equation. I am not going into the mathematics. You can see the mathematics. You will get this value. And what is this? This is, if you want to write now FDM, del U by del X प्लस डेल वी बाय डेल वाई, यू का किस पॉइंट पे निकाल रहे हो? पी के ऊपर. तो पी पे जब डेरिवेटिव निकालेंगे तो क्या होगा? यू ई माइनस यू डब्ल्यू बाय ट्वाइस डेल्टा एक्स प्लस वी नॉर्थ माइनस वी साउथ by twice delta y, right, is equal to 0. You are getting same equation. So whether you go by FDM or you go by FVM, you are getting same equation. But that is only a coincidence. Okay, this is just to verify that okay, we are following the right track. Okay. In this particular case where the equations are one dimensional, you find that your FDM and FVM are same, right? So this is what you get. Now I have missed this line here. Now if this grid is not uniform, now actually you have to find UE on the east surface. Now suppose the difference between these 2 points, matlab this distance from here to here and from here to here is not same. This is not equal. They are not equal to each other. So the point at which E point at which you want to find out, the east and the P point, they are not equidistant. So you cannot find it is at the half. You can take the weighted average. Linear interpolation you can do. So this term will become, this is where you are finding UE is equal to UP plus UE by, that will become weighted average. Or if you can go still advanced, that you can your own weightage you can add. Okay, on the right side I will give, when I am going out of the cell I will give more value to it than the left. So not only about the distance, you can give still more than the distance. You can give value let us say square of the distance, weight, or double the weight of the extra. So you can divide. You have to basically divide between, suppose I can give equal weight. Even if they are not equal, I can give equal weight. It's my convenience. Or I can give weight equal to their linear distance. Or I can give weight them equal to the square of the linear, or square root of the linear distance. Whatever way I think. Because these type of things happen later on. Right? The only thing is we have to find. So when we are talking about this cell, right, what we have done, we have found at point P, we tried to find the del u, these equation del u by del x. This was found at point P, and del u del v by del y was also found at point P. And for that, we have to take help of these 4 points, right? So, and then they are actually valued in terms of n, e, s, w, and this point. So this is how it goes about. It so happens that for this problem of one dimensional, FDM and FVM turns out to be same. It will not be same for other problems, okay? So it doesn't make a difference. The other thing we noted is that we don't know what is the truncation error here. That order we don't know. Now another 5 minutes I can take and finish there is no new concept in the thing. That we can also do the discretization of second order partial derivative. The only thing we have to do here is we have to write del square phi by del x as this. And del phi by del x you can write w. So this second derivative becomes a single derivative. Now this you can write in terms of FVM, it will be like this. Green's theorem, Gauss theorem you will apply, and you can write like this. And then you can replace this by this. So if you want to find the second derivative, it will be there. So this is the discretization of the second order derivative in terms of the first order derivative. And first order derivative you already know. You can find out. So this is how it is done. Same thing can be done in the y direction. Right? The first order derivative this are evaluated at the center of the corresponding surface AI of the cell and denotes the number of surfaces. Okay, well, same thing. Now if you have a question. May I summarize the whole thing? So the whole issue is here that we start with FDM. In FDM, we are talking in terms of points and not in terms of volumes, right? Although you can make volumes out of those points, but we are talking in terms of points. Now when we talk in terms of points, because we start from conservation equation, then we go to the algebraic equation, which are not same. So the algebraic equation which have been derived from the conservation equation may not be conserved. So the conservation is not maintained throughout the domain. Now we start another technique which is FVM, which talks in terms of volume only. And when it talks in terms of volume, so now we are applying the equation on the volume, cell of a volume of a cell, and we are applying the integral equation, and we are applying all those quantities: accumulation, advection, diffusion, and generation. So in that volume, though that physical quantity is conserved. So the first difference between FVM and FDM comes in FDM, the conservation at the point or at the cell level you don't know whether it is maintained or not, but in case of FVM it is ensured. The second thing is that because FVM is based on volume, you can have unstructured grid, while in case of FDM, you have to go for structured grid or break the domain into number of parts to have a structured grid, or you have to go for generalized coordinates to make a structured grid, because for each point you have to find the point on the left and point on the right, and this necessity is not there in case of FVM. So FVM has that advantage. So these are the two advantages. One is that you have conservation at cell level, and the second is that you can talk in terms of unstructured grid. But there is a disadvantage that in FVM you are doing approximation and interpolation both, and there is no clear equation for that. As a result, you are not able to know what is the level of error at each cell level, which is slightly complicated. So FDM can be made, formulation can be made from truncation error of order 1, 2, 3, 4 and so on. Of course, as you go on, it will become more and more complicated. That's a different issue. But you know the procedure. It has to be done once and then it can be replicated. But in case of FVM, you don't know, and that mathematics turned out to be difficult. So you don't know what is the order of error. Now then, when you apply it to FVM and FDM, it so happens then we found that in one case where we have this equation del u by del x is equal to del b by del y is equal to 0, if that equation you apply to a grid which is a uniform grid, a square grid, right, or let us say rectangular grid with a uniform spacing, then it turns out that FDM and FVM gives you the same solution. But that is just that is just to show that the things are similar. Of course, as you go forward, the formulations will become different. Okay. So this is all about FVM. Of course, we have one example also related to that. We will do it tomorrow. Okay? So I close here.